Actually, you will see this is exactly the same paper, the same reactor source, but recompiled today. You see, this is 2020, no longer 2012. So this is not the paper which is published by Elsevier. It's what they could have done. Now, if you go and check to the source code of the 29 lines, which is down here, the same code. Now, in the caption, you see simple implementation, and then between parentheses, slightly simplified from the actual code. Because when I tried to redo the exercise, I went back in the version control history of my code, looking for exactly these 29 lines, and I didn't find them. It never existed like this. The real code, and now you know the trick, okay, so it is the same sort of HashDB, is this one, which is a little bit longer than 29 lines, but we had the page limit in the paper, and so we decided to go and slash a bunch of things with error, correction, comment, something, so the code in the paper was not the code we were using, but now, you see, I can do the trick, so I can put something which is readable and then put it into something which is the real code of the other side. And we also did something else. You see, at the end, instead of just saying it is on Gitorius, now we say Gitorius also archived on software heritage, and now you have a pointer to the version of the project archived on software heritage on GitHub. No, sorry, on Gitorius. You see, this is a copy of the code that was on Gitorius. You also see that I am a good citizen, so when Gitorius was shut out, I added a README file that says moved to GitHub with a pointer to GitHub. But actually, people that were on holidays during the 3 weeks that Gitorius gave to people to move out, they came back and they didn't have time to do the good citizen stuff. Okay, it was a problem. Software just went away. So the idea is just to give you an idea, and if you want to know more about how to use this and how to do this in your paper very easily, the kind of trivia, you go on the software heritage webpage, here on archive, save research track, guidelines, how to have a very simple description, how to download the browser extension, how to create, for example, webhooks, to have automatically your software saved every time you do a commit or a revision, etc., how to get pointers to anything in there, how to get citation, how to use a citation extension. One pager, super easy, no rocket science at all, and yet we are still working with journals, conference proceedings, etc., that seems to be stuck in the 1990s. I think the way we do it. Zip files, star files, whatever, come on. So I hope I could convince you about this particular case. But this is maybe for you interesting for using this in your research just as a basic tool for doing the science. But I would like not to stop here. Okay. I would like to point you to something more interesting for you. Okay. This is just basic stuff. Adoption is dictatorial is taken. Let's move from software to research to research on software, which is a different area. So now that you have this huge archive with all the software public, software of the cloud, over 7 years in a unified data structure, what can you do? So let's start looking at the data sets that you can get from the archive. What happens is that since a few years we are regularly putting on AWS in the Open Data Collection a dump of the graph content systematically every year, then every 6 months, and now we are doing it more or less every 3 months, depending on the sources. It's very easy to access. You can go here. And so you look at this graph data set available, we can start asking questions about how people actually program or code or do things. And here, let me see if I can do it directly live, because we are still connected. Let me give an example. So a few years ago, I remember seeing an article in software engineering where people were asking a question which was basically, we would like to know what are the most popular commit verbs used by developer when they make a commit. But let me remind what this means. Okay, when you are doing software development using these kind of tools like Git, version compositor, etc., every time you get to a point that you can map the steps to be stored, you create something which is a commit, which is the status of the software, and you add a log comment, a comment there saying what this particular status is. Now, the good practice in industry that I propose in academia is to the text of the commit should complete the phrase this commit will. So you expect it to start with a verb. This commit will fix error number this. This commit will add functionality this and that. So people in software engineering wanted to know what was the most popular thing that people do. So I remember reading this paper, and this paper is like, okay, so we hired 2 postdocs, 4 PhD students, we bought a machine, we downloaded 150,000 projects from GitHub, I mean, which ones to most, but 150,000 projects. We built a pipeline, we ran this as an experiment, and after 12 months we get this result. Now that you have this data set, let's do the same. Let's do the experiment. Okay? So now, this paper can be described by this SQL query. So basically, it is a point. Okay. You select from the revision table the message field. You know, when there is the table that stores all the commits, there is a message field. Then you do a lot of mangling there, so you convert from to F8, you remove leading and trailing spaces, you split it or spaces, take the first one, the first word, put in lowercase, take the stem, I mean, typical thing, and you only take messages which are smaller than 1 megabyte. 1 megabyte. You won't believe it, that we find in the archive commit messages which are longer than 32 megabytes. Very common. Right? No, then you discover there are people that are putting in the commit message the data they use for the experiment or a small block system. But anyway, so okay, let's keep the more than 1 million character comment. You do this, and then this is standard SQL, so you count the number of occurrences, you group by word, you remove the words which are empty, you order them descendant, and then we can run it. Because this data set, which is hosted on AWS S3, is in a special format, which is ORC, which is color format, that you can use directly using this thingy, which is called Amazon Athena, which is the Amazon implementation of the Presto open source library that does massive SQL in a distributed cluster. Okay? Unfortunately, it doesn't have indexes, so it's not super efficient if you want to do sophisticated things, but scanning table is the best you can get. So I can just run it. Let's run it. And when we run it, I'm taking educated guesses from the audience. What do you expect to be the number?
Commit.
Commit.
Next.
Things?
Next.
Anything?
WIP.
Work in progress. Okay, nice. Anything?
First.
First. Initial.
10.
10?
10.
Wow. Okay. Now, here let me show you what is happening, okay? So, it is scanning the revision table from the dump of the graph that we made on April 19th, 2025. So, it is already scanning 162 gigabytes, actually finished, 43 seconds. For doing the analysis. What is the cost? Well, the cost model on Amazon Athena is that you pay only for the data that you scan. And the cost is $5 per terabyte. So we scanned 169 gigabytes. So how much does it cost? 60 cents, 70 cents, maybe? So, don't worry, my goal is not to put the PhD students students how to work. So my goal is to let you do intelligent things instead of stupid data mining, okay? So here is the result. Half a billion updates. The merge, the add and fix, and there is a winner here, fix, yeah, good chance. Add to bound, create, initial, there was an initial work, commit, you see, which is strange. This commit will, commit. Okay. Well, anyway, this was just to show you the kind of thing that you can do, this kind of thing, which are impossible to do in a reasonable time. And by the way, this is not 150,000 projects. This is 325 million projects in Western. But if you remember well, one course, are you happy with having an SQL interface to query a graph? No. Why? Use the structure, yes, but come on, we are PhD students in programming languages. Remember something from logic? Do you study some basic first-order logic? Remember this one nice result in first-order logic that the transitive closure of the binary relation is not expressible in first-order logic. Remember this? Maybe you say, but why should we learn these stupid things which is very abstract and has no value? No, this is telling you that using SQL, you cannot query a graph. If I want to have all the transitive descendant of the directory, there is no way of writing an SQL query to go there. Because SQL is a subset of first-order logic. Then you can use recursive queries or this kind of stuff, but they actually not work very well. So what happens if you want to do a study that actually uses the graph, just a table? So this is a skipping. Well, it turns out that 7 years ago, Stefano Zacchioli, another Italian that escaped from Italy for some reason, a very good friend of mine and co-founder of software with me, was on a scientific advisory board for a European project doing some stuff. And he met Sebastiano Vigna. This Sebastiano Vigna, together with Paolo Borghi, is one of the world experts on compressed data structure. You see, now we are getting there. And actually, he's the author of a framework which is called WebGraph. It is a framework for compressing the graph of the web that is used by Google, by Microsoft, by Facebook for the graph of the social network, etc. It is mind-boggling kind of algorithm with a lot of mathematics inside it. Then you end up with something. To compress this graph at the end, we are using 3.1 bit per arc, as in .1, but we did the average. And Sebastiano was very unhappy because he wrote the code, without the algorithm. Everybody from Google Data Company were using and said, thanks a lot and bye. So he never had the chance to try with a real graph. He discovered our graph and said, let's play with it. So after 6-7 years, now we have a beautiful pipeline, completely rewritten in Rust over last summer, that allows to take the full topology graph and fit it in less than half a terabyte of central memory. This means that you can visit the graph with the standard graph algorithm that you write in Rust. No need to go into SQL queries or recursive queries, etc. And here we have the pointer if you want. And it is not easy. It takes 3 weeks, and we need a 5 terabyte RAM machine in the middle of the pipeline for doing this. That's really revolutionary. And now we can do things like this, merging the access to the SQL version with the power of the graph visit to change the way people are doing research, for example, in software engineering. Let me give you an example with slides that come from, not from my team, from another team. This is another team, a team Riyadh, where SE is for software engineering. And they wanted to do some massive analysis of the quality of Android applications. So you want to get all the source code of all the Android application out there. How do you do it? So they tried this way to go and look for Android application on tons of different platforms. And then they said, let's try to use a software editor. And they did already the heavy lifting on removing the details. How does it work? I mean, to find the Android application, the telltale is a manifest file which is called Android manifest.xml. If you have something like this at the root of the source code, this is an Android application. So what they do? First of all, they did something similar to the query I showed you before. So you iterate over all of the directory nodes and check whether there is a directory node that contains something which is called Android.xml. Once you find it, you get the list of the software hashes of all the file contents that are associated with each file name. And this is very easy. You do it with the SQL query, super fast. But now you want to go up from the file content to the origin. This is a full graph traversal, so it doesn't work with SQL, and this is where they use the graph. I forgot to mention, the half terabyte is the graph both direction, okay? Top down, bottom up, so you can visit in the both direction. So doing this, they got it in a couple of days, everything was done. So the bottleneck for them, I mean, this is their software engineering, no GitHub bias, hundreds, thousands of different platforms. Very simple data structure, no need to understand the Git subversion, parsit, etc. Reproducibility is easy, you just publish the list of the hashes of the file that you have been using, you don't need to export the data because it is already in the archive. And we already did the work for everybody, so no need to go and scraping GitHub over and over and over again. By the way, they are really not happy on being scraped by AI bots right now. I will go back to this. So this is another example of thing that people do using this kind of graph. This work by Stefano and Davide Rossi. So they took the 50 years of development looking inside the graph. They looked at all the commits one by one, found the email address of the people, try to associate the email address to the country. .fr usually is France, .it is Italy, .org you don't know. All right? And then you check also some other heuristics of the time of the day of the commit. So if it is at 5 o'clock in the morning, either you are mishandling your sleep time, or maybe you are in another time zone. So trying to do this, and they got this kind of picture, which is pretty nice, because you see red and blue are Europe and US, and the other colors are all other countries in the world. So you see how now, today, in these days, over a third of the software developed around the world is neither developed in Europe nor in the US. Public software, we are not talking about proprietary software. And again, this was impossible to do without having this kind of graph. Another interesting thing for you, since you have the programming language this is a study we did with the person in my team in Inter this summer. We looked at the evolution of activity on programming languages. How do you do this? Actually, you take every single file content in the archive. You associate to the file content the most popular file name. There is not a single file name because we duplicate everything. So you take the most popular file name, you take the extension, this is an approximation for the programming language. And then you need to know when it was first created. And how do you do it? You visit the full graph, you populate the timestamps on the commits. You will get leaves and you keep only the earliest part. After you do this, you can get this kind of picture. Actually, in the paper you find tons of pictures. And you see the rise and fall of Java, for example, and these kind of things. The explosion of JSON, I agree, JSON is not a programming language, but anyway, it's data form. This doesn't mean that the amount of software is small. These are examples. Okay, so you need the number of modification of C files today is in percentage much smaller than the number of modification of programming languages. But the evolution of source code is explosive. Again, using the graph, you can get this kind of picture, and you see that every 2 years, the amount of original source code change doubles. So and this was before AI. So let's see what happens in a couple of years. And then last but not least, let me show this other pointer maybe for moving to the more interesting things. Now that we have this graph, we are kind of curious. I mean, can we use it to raise awareness about the production of software from academic institutions? To make it visible how many contributions a particular university, a particular research center has made to software development today? Well, why not? So step number one, let's say we are looking for Berkeley. We have 5 billion commits. I think over the 5 billion commits, in color, all the one that there is at least one email address of a contributor coming from Berkeley. Then you go from the top of the graph, there are 385 million projects. One by one, you go down in the graph and you count all the commits that are covered. Okay? So you can know how many contributions come from that institution. Of course, we get tons of duplicates in the origin because the origins are duplicated. So now when you need to clustering, representative elicitation, etc., etc., you can add some other information. And this, for example, is a picture from Berkeley. So for the Berkeley University, not very far. In the south, you get contribution since epoch. January 1st, 1970, this is when the Unix system was basically created. You remember Berkeley standard distribution? Berkeley had a really important role to play in Unix. Almost 30,000 different contributors and 2.5 million commits. And then you can go more and say, what are the top repositories with contribution from people in Berkeley? You can go on and look at the different kind of things that are there. Now, for example, do you know Boeing? You remember SETI at home? Yes, again? Well, Boeing is a kind of modern version of SETI at home. This one is a tool which is used to monitor cluster, and this one, I mean, the Unix history repository, this is a synthetic repository that has been resolved with all the history of the Unix system, and of course there are tons of contribution for that tool that we was major contributor. So you see, it gives you an idea of what you can start doing using the archive as a telescope. So now we are trying to take a picture of the sky. The picture of the sky is when you look at globally what is going on, so the energy, etc. And then you can take a picture of a planetary system. You focus on Berkeley, on Stanford, on MIT, on Harvard, on India. I played with a bunch of places, but I don't have time to show you. That is kind of impressive, just to say, one of the biggest ones. This is a typical, simple example of application. But you can do more. For example, think about cyber security. Probably, since you are working in programming languages, you are very focused on what I call the vertical approach to security. That is to say, analyzing one project by project, checking whether there are vulnerabilities, errors, mistakes. For example, the last course we had on abstract interpretation is a way of detecting problems in a piece of code, overflows, this kind of thing. I abstracted the model where you run the problem. But there is also another issue, which is horizontal approach to cybersecurity. To understand what this means, we need to look at how software is actually built today. So when I was a student in your place, 40 years ago, people were basically building software from scratch every time. The big revolution that appeared with the explosion of the use of open source is that nobody ever write a piece of software from scratch today. We all reuse hundreds of components off the shelf that you find somewhere as open source component on the place. Take the case, I don't know if you have an iPhone, because Apple is considered the most closed ecosystem today. If you have an iPhone, go on General Information Legal, browse it, and look at how many different open source licenses are mentioned in there. inside your iPhone, inside your Mac, you have a Mac, there are tons of open source components. Okay? And these come from all over the place. So you have tons of dependencies. And so, you know, you remember this picture, no? This picture here was very famous, this KCD. It was when there was the OPLSS problem that was related to the fact that OPLSS, the most used piece of software in the planet, was maintained by just one person on his spare time in Nebraska. Okay? And now with cybersecurity, imagine instead of some random person, imagine it is some evil person that actually maintains a major dependency for everybody and inserts some vulnerability. That's the mess. And actually, this is actually happening a lot of time. XZ, you heard about XZ, I mean, this was a compression, it is a compression language that was maintained by, again, very little people. And it was an incredible social attack mounted on them, so people trying sending support, you have an issue here, you didn't have time to fix that, putting pressure on the developer until the maintainer cracked and the one providing all these records saying, do you want a hand? Yes, sure. So he got access to the main branch of the software and started introducing vulnerabilities that were discovered completely randomly by a Microsoft developer that saw that using XZ the system was a bit slower than before. And after analyzing, we found that there was a vulnerability. So this is a major problem for cybersecurity today. So and you do not have time or the resources to analyze all of your dependencies on your software. You can check yours, but everything is complicated. So this is one particular application that we actually is developed by Stefan and people in his team, is to study one-day vulnerabilities. You know, zero-day vulnerabilities are the ones that you don't know. One-day vulnerabilities are vulnerabilities which are known somewhere, but not fixed elsewhere. And so typically, this is an issue when we are doing open source, because you may have a very well-maintained project. I mean, Keyword is a game which is pretty popular, if you know. And at some moment, somebody makes a fork on this project, digging at another real thing. And at some moment in time, you see that in Keyword, somebody discovered a vulnerability, so all of this code was vulnerable, and they introduce a patch. Okay. But unfortunately, DDNet was forked before the discovery of vulnerability, and didn't get the patch. Actually, get the patch much later. So essentially, all this history is vulnerable. How do you spot it? Well, today, we use tools like OSV.dev, which is maintained by Google, that aggregates information of vulnerability associated to commits. But this analysis is done project by project. They do not take into account forks, because they don't have a global view of the world. But the graph we provide provides a global view of the world. And so what we did, I mean, actually what Stefano did was to take the vulnerabilities and cover and follow the graph completely and find all the other vulnerable things. So they identified 2 million forks potentially vulnerable, tens of millions of potentially vulnerables, a lot of them vulnerable in the last version, and then you cannot, I mean, we do not have the resources to check millions of repositories. Okay, so they checked a few dozens and found real vulnerabilities that were invisible to all the models, including from the hyperscalers. So this research work has been finished, and we are planning to include it in the services of software which in the company. You know that between a research project and something that runs 24/7, etc., there is a big job. Okay, so we need to take time to engineer the project. Now, let me skip it here. I'm sorry, I'm putting a lot of stuff on the table, but I cannot avoid talking about AI. If I don't tell you something about AI, you will say that I'm living in another world. And so I need to tell you more about AI. So, okay, let's see where AI comes in all this story. But let me recap first. You have seen the origin motivation is a philosophy. Software is very important. Source code is essential. It not contain our knowledge. It's not enough to keep just because we need also to code source code. We started this crazy idea of creating the archive of everything 10 years ago. And we slowly went over and so providing a tool for open science, for providing access to research and research. Then we discovered we could do more, so creating data sets, people can do analysis, and this analysis started to give a bunch of examples, etc. And they come from software engineering to vulnerability cracking and cyber security. And then a couple of years ago, actually 3 years ago, after ChatGPT exploded the world, we got contacted by people who wanted to use the software package archive as a data source for training models. For obvious reasons. Okay, so we get everything, we duplicate, we feed up the data. So we do for free for them a lot of stuff. What should we do? So our mission is a long-term mission at the service of human archive. And then you have hyperscaler, other people coming and say, oh, very nice what you did, then we get a copy to do machine learning, so complicated. So we ended up with 3 key principles for collaborating with entities or companies or research institutions who want to use archive for building models. The principles are very simple. So one is, since you want to get a copy of the knowledge of humankind, I think you should give it back. So if you train a foundational model, the foundational model should be given back. What does it mean? At least open weights. Okay? At least I want to be able to run it on my machine. Asking for more is debatable because also if they give me more, training a model costs $200 million. I mean, cannot really do it, and I want to have them to do it. Second, we want full transparency. So if you use 100 million files in the archive, you need to tell which one we are using. For copyright issues, or any other, for bias, or for whatever. I mean, we cannot guarantee copyright or bias, but at least we want people using it to be transparent what they do. And this is now easy, because you just publish, you use 1 million files, publish the file in 1 million hashes. That's it. No complication. Last but not least, since this is still very, very sensitive as an issue of AI in the world, we want these entities or companies to put in place an opt-out mechanism. So if somebody doesn't want to have their code used in the training, there must be a way for telling this, a way for these companies to remove the code before the next training. You cannot detrain a model, but at least for the next version, you should respect the author. We publish this in October 2023, and then you wait, because maybe nobody cares. Okay? And you ask for this, very nice. Nice virtual security, but who cares? Luckily, somebody actually accepted